been associated with what I'll call incompatible observables. In particular, X and P, or equivalently A and A dagger, which aren't really the observables in the sense that we can't measure the basis that way. And this notion of incompatibility has been related to the point that, you know, there is no joint probability distribution for definite simultaneous outcome in X and P. We could measure something that would say would be having a certain value of X and a certain value of P at the same time, but we never can have a definite outcome for that. It will be a noisy measurement by definition. And when we try to find these joint probability distributions, we generally fail. And that's related to the whole question of negativity of the quasi-probability distribution. And there's an intimately related aspect of this, which we won't talk about here, but I'll just mention. Which is sometimes known as contextuality. That is to say, the measurement outcomes we get depends on the context of other measurements we could do at the same time or not. And the fact that measurement outcomes are contextual is a distinction between quantum and classical statistical outcomes. Okay, so these are some of the sort of secret sauces that we think about as things that distinguish quantum from classical statistical outcomes. But things get we have other aspects that we haven't talked about associated with multiple degrees of freedom. And that most important feature that distinguishes quantum from classical is entanglement. Okay, something we haven't really talked about. And the interrelationship between these is an interesting question. What is really important? Entanglement, contextuality, negativity. And there's been important research programs that have tried to understand the interrelationship between them, and which really is that. I mentioned particularly Robert Rausendorf, who I think has been really one of the deepest thinkers along these lines. So entanglement is clearly, we've heard about it, we know about it, an important feature, but we haven't really talked about it here. It's something you've probably seen in your previous quantum mechanics courses or other courses in quantum information science, but it's not something that everyone has seen in great detail, so I'm going to just review some of the basics here today. And then what we're going to talk about through the rest of the lectures before spring break is how one creates entangled states of light in quantum optics and their implications in thinking about foundations and applications in quantum information processing. Okay, so that's where we're headed. Right. So, in particular, so let's just talk about entanglement is related to the question of correlations. Are the measurement outcomes correlated or are they not? And are those correlations that we see different from the kinds of correlations we see in classical statistical physics? So let's just think about the first example of just 2 degrees of freedom thought about as 2 particles on a line, particle A and particle B, which has some position and momentum classically. Okay? So this is 2 degrees of freedom. And if I wanted to think about the joint probability distributions, well, of course, I can think about that for either one or the other of position and momentum. I could think about the wave function that would tell me about the joint measurement outcomes of, say, the position of particle A and the position of particle B. And I could think about the joint probability distribution of those measurements as the square of the wave function. And I can think about the marginal probability distribution, the probability of finding X irrespective of what the position of particle B is. Or similarly, I could think about the marginal for the probability distribution of position of particle B irrespective of particle A. And the question is, are these correlated or not, right? So we would say that these are statistically independent outcomes if the probability distribution for the joint outcomes is the product of the probability distributions for the 2. And the question, one could ask the question, under what conditions can I write this probability distribution for the marginal as the square of some wave function that describes the outcomes for particle A So when is this true? And the answer is if and only if the wave function is a product state. Now it's not exactly true. I could always just take the square root of this and times the square root of that, and that would give me the same thing. But it has to also be true for any measurement that I could do on this. I could have done a momentum measurement on A and a momentum or whatever I wanted to do. And the question is, when can I write the joint wave function that describes this as a product state if and only if this factorizes, okay? So, if the measurement outcomes are statistically independent, then the wave function is a product state. And if it's not statistically independent, they're correlated, then the wave function is not a product state. And in that case, we say that it's entangled. Now, that sounds heavy-handed. I mean, we're just saying that it's not statistically independent. And so what? We know that there can be lots of things in classical physics where the measurement outcomes of two different random variables are statistically correlated. But as we know, and I'm sure you've seen, there's more to it than this. But it's kind of interesting that for the case of assuming this is true, that there's this intimate relationship between correlated or not and a product state or not. Now, this is true only for pure states. It's a much more complicated and subtle point to distinguish correlation from entanglement. But if we say that the overall state of the system is a pure state, then there's one or the other. Either it's completely uncorrelated or it's entangled. Whereas as what we have, as we'll see a little bit, we're not going to talk about it because it's a very complicated subject and not really the subject of our course, that when you have the overall state of the system, of the joint state of the system is mixed, there can be a situation in which the measurement outcomes are correlated, but it's not entangled. Okay? So in some sense, entanglement is a little bit of a sometimes overstated aspect of the magic of quantum mechanics. And what is really important isn't necessarily entanglement, although 98.735% of all papers in quantum information start with entanglement is the key to, quantum computing. Well, maybe. Okay. We'll come.
It's part of the essential.
The other 1% is like, once we have error correction.
Yeah, that's right.
You want your paper to be accepted, so you have to start this way.
Yeah, that was true at one point. We know better. Okay, so let's just remind ourselves that we can think about this notion of entanglement versus separable or product state from an algebraic point of view. And that's the important ingredient there is the tensor product. So in quantum mechanics, generally, instead of thinking about degrees of freedom, we often call them subsystems. Each subsystem is kind of what classically we would call a degree of freedom. And if I have two subsystems, there are two parts, we call that a bipartite system. And the bipartite Hilbert space of the two parts, A and B, we'll write as a tensor product space of a Hilbert space for subsystem A and a Hilbert space for subsystem B. Okay. Where this is the tensor product. And we define the tensor product such that if we have a state psi in Hilbert space A and a state phi in Hilbert space B, then we define a state in the joint system as the tensor product as such. Okay? And with that, we can define, for example, if E sub I I goes from 1 to the dimension of subsystem A, and f sub j, j goes from the dimension from 1 up to the dimension of B, is our bases then we can define a a product basis as a basis for the joint Hilbert space, right? So if the dimension of Hilbert space A is D sub A, and the dimension is B for Hilbert space B, then the dimension of the joint space is the product of the dimension, right? So the dimension of this is the product of the two dimensions. And obviously that reminds us that when we have multiple subsystems, the dimension grows very fast. It will grow exponentially with the number of subsystems. Right. And we can define the inner product on the if I have two states, say psi tensor phi, and I look at the inner product with another state, chi tensor eta, that this is just the product of the complex numbers, that is the inner product of the two. And from that, we have representations. So if I have a general state, okay, so let me just say, such a state here is called a product state, or an unentangled state, or a separable state. For a pure state, these are all the same thing. If it's not true, then we say it's an entangled state. So if I have a general state, maybe entangled, and I express that state in the basis, I sum over the total dimension with expansion coefficients where the expansion coefficients are that, right? Okay. Moreover, we can talk about the operator, tensor product of observables, or operators. Doesn't have to be observables. So I can define an operator or matrix MAB as, say, O on A and N on B. That tensor product is such that if this acts on a tensor product of vectors, it's the action of this on the first operator and this on the second state. And that with those rules and the tensor product, we can write matrix representations, right? I'm not going to go through that. I hope you've seen it, how you take the matrix representations of tensor products of matrices. Okay, so now we can ask the following question. We can ask about marginals. So let's say I have some joint probability distribution of seeing outcome I and J on the system where I've measured in the basis, that particular basis. So this is the joint probability of measuring outcome I on system A and outcome J on system B. If I measure them, I can do this measurement because this is a basis. Okay. Of course, this is also equal to the diagonal matrix element of the density operator, as it must be because it's the Born rule, where rho AB is the density operator associated with the joint state, in this case, a pure state. Okay, so that's the joint probability distribution, similar to what we're thinking about from the point of view of wave mechanics. Okay, and now I want to talk about the marginals. Let's say, what's the probability of measuring I on system A, irrespective of what I measure in B? How, from statistics, how do I find that marginal? Well, I have to marginalize, which means I sum over all the outcomes. Okay, that's the marginal probability distribution, right? And that is equal to that, right? According to this. This is called the partial trace. Of course, if I sum over I, and now I'd have a, I sum over I, that would be the trace of the matrix. And the trace of the matrix is the sum of its diagonal matrix elements, which, if it's normalized, is 1. But the partial trace is the marginal, gives me the marginal probabilities. Okay? I wanted to remind you, because people think about this in some very complicated quantum, it's just statistics, okay? So if I'm looking at the marginal distribution, I just sum over those probability distribution, but that is not the whole trace, it's the partial trace. Okay. So I obtain, not the partial trace, the marginal probability distribution through the partial trace of the insertion. Now, as we know, any probability distribution in quantum mechanics, any probability of any measurement outcomes, so this is the probability of measuring outcome I on subsystem A POVM is just the basis of A. So that's what that is, right? And that should be given by Born's rule. And that Born's rule should be the trace of something that's associated with the state of A times the POVM element. That's our rule for the diagonal matrix element, in this case for a basis measurement of that sort. So the question is, what is the marginal state? If this is the joint state of the system, this is the state of the bipartite system, A and B together, and this tells me the probability distribution of a particular joint measurement. I want to know what is the marginal state. The marginal state is the quantum mechanical generalization of the marginal probability distribution that we wrote down in statistics. This was the marginal probability distribution associated with a particular set of measurement outcomes, whereas the marginal state of the quantum system is something I could use to calculate the measurement outcomes for any POVM or any measurement I could do on subsystem A. But we can see what that is from this, because what I see here is that P sub I is equal to, if I look at this, I can fact from, well, I'll write it out again. What's written over there, I'll just write again for my own convenience, maybe yours. That's what's just written over there, I just rewrote it. But that is equal to sum over ij E sub I tensor F sub j rho A B
It's just the sum over J, right?
Excuse me, yes. Thank you. Okay. But I can rewrite this and think about this as the matrix element of this object. What's written in here looks like a matrix element, but it ain't. It's a partial matrix element because I'm only taking the matrix element with respect to B, and it's still got something left over with respect to A. And so this is the partial trace as a operator rather than a matrix element. And so what this tells me is that the marginal state I get by the trace over subsystem B of the joint state. And the language we often use is that I trace out one of the subsystems. When I've traced out that subsystem, I've left with the marginal state for the remaining systems, the remaining subsystems. So these are all different pieces of mathematics that are describing the same thing. By the way, this is often called the reduced density matrix, or the reduced density operator. It's the same thing. But I really like this term better because it is what, it's a much more evocative term that is telling me what it is. It's the marginal density operator, it's the marginal state. So averaging out the other degrees of freedom is equivalent to tracing over the matrix partially for those part of the substance. The partial trace gives me that. All right. Let me remind myself of what else I wanted to say. Blah, 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 blah. Good. All right. So now with some of these tools in place, we have the question of entangled states are ones where the joint state of the system as a pure state does not equal a product state. For some now, how would we know whether the state is entangled or not, whether that's true or not? Yeah?
Can't you see it in negative function?
Oh gosh, that could be complicated. Not necessarily. First of all, we might be able to think about the Wigner function associated with, say, two modes of the electromagnetic field, where we thought about the Wigner function jointly for x and p. But as we'll actually see for a moment, if I have an entangled state, such as a two-mode squeezed vacuum, that state is an entangled state in terms of as we will see, there's a entanglement between the quadratures. The quadrature outcomes of a two-mode squeeze state are entangled. But the Wigner function is positive. So there's something weird about this. We'll come back. That's really kind of, it's kind of an interesting point. We'll come back to that. It's really also related to one of the things that EPR got wrong, but I'll leave that as a little teaser for the moment. Let's look at the case as we often do. Let's consider two qubits. Okay, so my joint Hilbert space is the Hilbert space associated with two spin 1/2 particles. And so we have, for example, a basis might be the four-dimensional Hilbert space spanned by these four vectors, where this is the tensor product. Say this is up is eigenstate of sigma z. Okay, so there's a basis. I'll write down a state. Is that state separable or entangled? It's not obvious. If you stare at it long enough, you might, if I did this right, this little check is, I believe, this. That's to say, this is a product state of spin up along X and spin down along Y. Because spin up along X, we all remember, is up plus down along Z over root 2, or actually up along Y. And spin up along Y is up plus I down along. And if I look at the tensor product of this times this, and this times this, and this times this, and then this times this, right? So, it's not obvious by just looking at a state whether it's entangled or not. Okay. We're going to come back to that to say how we quantify. First of all, how do we identify, to remind ourselves, whether the state is entangled or not? And moreover, quantify the amount of entanglement, the amount of correlations there are. All right. Let's talk a little bit about quantum versus classical correlations. So one of the most famous entangled states of two spin 1/2 particles is a spin singlet, which is the spin s equals 0, ms equals 0 state of two spins, which is up, down, minus down, up. This is an entangled state. There's no way we can write this state as a product state, okay? And often we think about, I'll just emphasize here that these computational basis states, as we like to call them in information, are spin up and spin down along Z, okay? These spins are obviously have a kind of correlation. They have an anti-correlation. So we know that if Alice, the keeper of spin A, measures in sigma z basis, she'll find up or down with probability 1/2. We see that because of this probability amplitude. There's a half of the amplitude get up and the amplitude get down, right? The post-measurement state well, if she measures in the sigma z basis, suppose she gets spin up along along Z for her spin. And I want to say, what's the post-measurement state? How would I find that? Well, it's a projective measurement, right? So I would say I'm only measuring on my subsystem. I'm Alice. This is my projector. I project onto that state, and then I normalize, renormalize. Okay. And when I do that, what I see is what? Well, I project, I only pick up this thing. That means Alice state, and once I renormalize, I'll get rid of this half. And so the post-measurement state is Alice's spin is left up in A, and Bob's spin is most certainly spin down along C, right? Which means, in this case, if Bob were to do a measurement on his spin, he is 100% guaranteed to get spin down. So there is this particular anticorrelation. And similarly, if Alice finds spin down along C, which happens with probability 1/2, then the state of the system gets projected onto the spin down outcome. Which means Bob will find spin up along Z with probability 1. Right? So there's an anti-correlation in this case. If Alice finds spin up, Bob is certainly going to find spin down along C. And if Alice measures and finds spin down, Bob is guaranteed to find spin up. Okay? But so what? I mean, you know, we have those kinds of correlations all the time. Okay, there's two. One is orange, one is black. Tim, give me your hand. Okay. Keep your eyes closed. Okay. One of them was orange, the other one was black. Open your hand, see your color. You had a 50-50 chance, right, of getting black or orange. So tell me, what color is mine?
Black.
It's guaranteed. Surprise! Right? You know, the fact that you can predict something that was, I could have been on the other side of the galaxy, and you could certainly have predicted that that was going to be true, is just the fact that they had this anti-correlation between them, and we knew it together. We were together at the same time. I put in your hand, and then I went over there, and then you can predict. And so there are states like that all the time. I mean, I could write down this state here is a joint state of two spins that are correlated. they're anti-correlated, if you like. Alice and Bob's spins are anti-correlated. If Alice measures spin up along Z, Bob will find spin down, vice versa. But is this state the same thing as the singlet? No. The singlet state is that. And that state is going to have the cross terms in it that are related in some sense to quantum interference, right? And what's the difference between the predictions of the measurement outcomes that can happen along this versus what happens if the state were this? These two states predict the same set of measurement outcomes when Alice and Bob do this measurement. But they could do a different set of measurements. And they have to have different predictions, otherwise they would be the same state, and they're clearly not. And what's special about the singlet is that it doesn't matter if I write a spin up along any direction in space, which you'll remember, if n is a vector, some direction n on the unit sphere, which has polar angles theta and phi, I can always write spin up and spin down along that direction as a superposition of spin up and spin down along z. Who remembers how to write that superposition in terms of theta and phi?
There's theta.
There's thetas. There's a cosine theta over 2, spin up, right? And then e to the I phi sine phi over 2, spin down along z. And similarly, the ones who spin down is going to be that's the spin down guy. And the singlet state is anti-correlated along any direction in space. Not just along the z-axis. So no matter what direction I measured, I would find this anti-correlation. And that wouldn't be true for this. In some sense, the quantum system has a stronger sense of correlation that we're going to see has very profound implications about whether that cap in Tim's hand actually had a color all along, or somehow, I don't know what. I really don't. Okay. So, with that said, we want to say what we want to finally remind ourselves in this overview and introduction, for those who haven't seen it all before, to entanglement. We want to ask the question, is the state entangled or not? And if so, how entangled is it? Okay? And a pure state. We ask the question, how entangled is it? So I have a tensor product space, two subsystems, dimension D sub A, dimension D sub B. They could both be infinity. They could both be dimension 2. One could be dimension 2, the other infinity. One could be dimension 5, the other dimension 7. It doesn't matter. Okay. And I have a pure state in this space. The whole story about entanglement of pure states is the story of the Schmidt decomposition. And everybody who learns quantum mechanics needs to understand the Schmidt decomposition. It's just so fundamental to the basic understanding of quantum mechanics. Okay, so let me tell you what the Schmidt decomposition is, and then we'll see where we get today. Okay. So the Schmidt decomposition says the following. This state can be written as a sum, u equals 1 to some maximum number I'll call chi, lambda sub mu, v or u sub mu for subsystem A, tensor v sub mu for subsystem B. So this is a particular decomposition of the state into a tensor product of vectors where the following things are true. Mu is somewhere between 1 and d less than, where this is equal to the minimum of dA and dB, whichever is smaller. That's the maximum possible value that chi can take. And this is called the Schmidt rank, or the Schmidt number. I like the term Schmidt rank. Okay? That's the number of non-zero lambdas. The set of lambdas, which are all real numbers that are greater than 0, the ones that are 0 don't contribute to the sum, are called the Schmidt numbers. And these vectors are called the Schmidt vectors. They're orthogonal and typically normalized. This one is for subsystem A, and this is for subsystem B. Okay, so the first point is that this exists and has its properties. We'll derive it in a moment or Thursday. But let's just, for the moment, say, okay, fine, Deutsch, this is true. What are the implications of this? Okay. Firstly, if chi equals 1, then the state is separable, unentangled. Okay. So we can find out whether the state is entangled or not by finding the Schmidt decomposition, and if there's only one Schmidt number that's non-zero, if the Schmidt rank is 1, then it's a product state, or unentangled. What else do I want to say? We can ask the question, what's the marginal states? write, to do that, we need to write the density operator and take its partial trace, because that's how we got the marginal. So let's write the joint state of the system. So what is the marginal state? Let's say the reduced density operator. I trace over B. Right? But tracing over B is the tracing over this. And the trace of this is a delta function, right? Because of what we just wrote over there. So this is equal to sum over mu lambda squared right? And similarly, what is the marginal of subsystem B? I trace out system A, subsystem A, do the same thing, and I'll get this, right? So that's really interesting. What do we learn from this? We learn two things. Well, we learn lots of things, but we learn at least two. One is that the spectrum of the two marginals is the same. Let's say the eigenvalues of the density operator of the marginal are the same. The two subsystems have the same spectrum, let's say the same eigenvalues. The other thing we have is that the Schmidt vectors are the eigenvectors So one way I can think about finding, at least getting a good way towards the Schmidt decomposition, is that I take the state, I take the partial trace, and I diagonalize the two matrices. When I do that, I get the eigenvalues and eigenvectors. I could say that the Schmidt numbers are the square roots, the positive square roots of the eigenvectors of the marginal states, or the reduced density operators, and the Schmidt vectors are the eigenvectors. Although there's one thing that's missing here, because this thing has some phase information buried in it. Because the Schmidt vectors have to have a definite phase. If these are going to be real numbers that are positive, the Schmidt vectors have to have some well-defined relative phase relative to one another. Whereas we had no information about that phase here, okay? And that is to say, we can't reconstruct the total state from the marginals. And this is an important point, and I want to emphasize this. This is something completely wacky and different about quantum mechanics that is not true in the classical world. And I want to understand the implications of it. Yes,
So, it's only separable if the Schmidt rank is
one.
1?
That means there's only one non-zero eigenvalue, which means that the marginal states, so if the Schmidt rank were 1,
Is there like a physical intuition as to why any system with like more than one non-zero eigenvalue has to be entangled?
yeah, well, it's for the very reason that anything that's not a product state, that's a pure state, is necessarily a correlated state. And anything that's correlated, if it's a pure state, is entangled. Everything. There's no way you can have measurement outcomes between two different degrees of freedom correlated in quantum mechanics without them being entangled. That's just the way it is. That's not true if we add noise into the system. That's a more complicated story. We can have a situation, and what we mean by entanglement is a whole, God, you know, I wish we had weeks to talk about that. But that's a very important and complicated story, what we mean by correlation versus what we mean by entanglement. But if the state of the system is pure, then correlation equals entanglement. And the only thing that's uncorrelated is a product state.
This is like a 2.
Like one is spin up along X and the other spin up along, you know, Z.
Well, but like what if I had like 5 particles?
Oh God,
Like
oh God, oh God, yeah. No, I can talk about various different ways. That's even a more complicated story. Multi-partite entanglement. God save me. But you know, but we can talk about chopping it up in many different ways, and that's the whole story of tensor networks. And I don't want to talk about that now. Right.
Maybe a short version says, like, we have for the Schmidt decomposition for a bipartite system,
Right.
we have this nice construction. The moment you go to 3 systems, you don't have this kind of nice construction.
That's right.
Oh, no, but for 3 systems, you have a similar construction.
Yeah.
Instead of something like this, you have like 5 times. So this is like a single, or at least for qubits, right?
Yeah.
In 3 qubits, you have a similar construction.
You do.
Yeah,
You
you
do.
do have generalizations.
You do.
But you don't have this nice.
It becomes more complicated very quickly, and then it really goes.
Different story.
It's a whole nother story. I want to emphasize some of the basics first before we say, well, what about everything else that I don't know? Because we don't understand the basics and we don't understand anything. Okay? Okay, so let's, what was I going to say? Oh, yeah. So the purity of the marginal is the trace of rho squared, which is the same for both of them. And if I call this square of this eigenvalue p mu, that's the probability of finding that state in the eigenvalue of the density operator, right? This is, of course, the sum of mu of p mu squared. Okay. If the purity is 1, then the marginal state was a pure state, which is to say that we had a separable state. That's the case where the Schmidt rank is 1. What's the least pure it could be?
1 over the dimension squared?
So let's think about this carefully. It depends on the biggest value that chi can be. The biggest value that chi can be is called d sub less than, right? And if I have something which is a completely mixed state of that, then that's 1 over d less than, right? That's the minimum. That would be the most entangled. So, there's this inverse relationship between the purity of the marginals and the degree of entanglement. The more entangled the joint system is, the more mixed the marginals are. Okay? And what that's saying is that I can have a situation, let's suppose that dA equals dB is some dimension d. The maximally entangled state would be an equal superposition of all the basis vectors whose marginals would be completely mixed. Where this is the identity in d dimensions. Okay? So what that's saying is that, I mean, this is nuts. Why is it nuts? It's saying that we have no information about the subsystems, but maximum knowledge of the joint system. That's saying, if I look at the individual parts, I know nothing. It's completely noise. It's completely random. But if I somehow had all the pieces connected together, then there are outcomes I can predict that are going to happen with, say, 100% probability, which is, say, the projector along that direction. And that's just not, makes no sense. I mean, classically, we can't have a situation where we know absolutely nothing about the parts, but everything about the whole. Yeah.
So when it's maximally entangled, that means Bob will always get anti-correlated with Alice, always. Is that right?
So for that particular, not for every entangled state, this is one such example. I could have a different one where they're correlated.
Well, no, I know, they can,
Yeah.
but they're either correlated or anti-correlated 100% of the time
Yeah.
if it's maximally entangled.
Ah, okay. So I think it's important that we want to get lots of different jargon straight. This business of being maximally mixed for the marginals is the case that the subsystems are maximally entangled. So there will be some particular definite correlation. As an example, I could have complete correlation or anti-correlation. It doesn't also have to be spin up or spin down.
Yeah.
It could be anything, but you're right. Whatever, if the subsystems are, what this is saying, so let's think about what this is saying. What this is saying is that no matter what measurement Alice or Bob does, it's completely random.
Yeah.
In whatever basis they do it, whether they measure along X, along Y, along Z, or whatever they are, they have just complete noise. That is related to the fact that, now I could have this state. So just because they both have complete noise doesn't mean that they're entangled. This is a little bit confusing, right? This is two completely mixed states. This relationship between the noisiness of the subsystems and the entanglement of the joint was only true if the total system were pure. In this case, the total system ain't pure, it's mixed. There's no entanglement here, but it's also true that their subsystems are completely noisy. So it's just a little bit complicated. Yes?
I'm not sure. You said that classically we don't have any situation where we know like more about the whole system than individual systems. But if you think about like thermodynamics, right? You can predict stuff about the global properties of like the pressure, temperature, entropy, whatever, of an ideal gas. But you don't even ever have to do statistical mechanics where you have to understand that there's a whole bunch of like molecules bouncing around. So where am I misunderstanding what you're saying, I guess?
What I'm saying is I can't have a situation where the entire system is pure, which is to say the probability of any microconfiguration of everything
Okay.
is completely determined.
Gotcha. Okay.
That's what I mean
Okay.
by that.
So it's
That's-
like I give you a microstate.
So you took exactly. So I have the joint, what it's to say is that the total system, every position of momentum is definite.
Yes. Okay.
In that case, well, that's true if I looked at any subsystem.
Yes, thank you.
That's what that means. Okay, I want to conclude with maybe one other piece of this story, just to continue about the general properties. So one way of quantifying how entangled the pure state is by looking at how noisy or how much information I'm missing in the marginals. So the degree of entanglement of the joint pure state is quantified by the missing information in the marginals. And the way that we quantify missing information is with the Shannon entropy. So the Shannon entropy tells me how much information I need to complete my description. And that entropy is the entropy associated with this probability distribution, and that's minus P log P. What base I choose is up to me. I can measure it in log base 2, and then I'd say how many bits do I need to complete, okay? But what is that equal to? That is equal to the relative to this operator. I can think about that as the trace which is known as the von Neumann entropy. So the von Neumann entropy of the state is the Shannon entropy of its eigenvalues. And that is a measure of how entangled the state is. It's what we call an entanglement monotone. And it's the best way of us quantifying how much entanglement there is in the state. And what's the maximum this can be? Well, the log of d less than, right? And the minimum is 0. So if the von Neumann entropy is 0, that means that the marginals are pure states. If the marginals are pure states, and then the joint system must have been a product state. Whereas if the joint system was entangled, the maximum it could be, this is how many bits of entanglement I have in the system, if I measure it log base 2.
So Shannon and von Neumann are the same?
They're the same
Same, but
with respect to, when I write this, this is equal to the Shannon entropy of that probability distribution. The Shannon entropy is the entropy defined relative to a particular probability distribution. So that is, in this case, this von Neumann entropy is the same thing as the Shannon entropy with respect to the
For this
eigenvalues.
particular case.
Yeah.
Like you can prove that it is in some sense the best probability distribution for getting this.
Yeah, in some sense, we can think about that. Okay, good. We'll complete there. So this is something everybody should know and think about and understand. Because if you don't understand this, you don't understand nothing about entanglement. And then we have to prove this. That won't be too hard. It's a little bit of linear algebra. And then what we're going to talk about for the remainder before spring break, or actually not before spring break, yeah, I guess before spring break, because I have to go to lunch, is how we make entangled states in quantum optics. All right. Have a good rest of your day.